Bismillahirrahmanirrahim. Welcome back to my channel. This video is about amplitude modulation, how I can make amplitude modulated transmitter using GNU Radio. So I'm just going to simply go over some math, and the reason that I wanted to show you this maths behind it, because I just want to take this mathematical equation and I just want to transform this as is using GNU Radio. Because what GNU Radio allows me to do is actually to look at my equation and just transfer that equation as is in a form of a flow graph. And if the math is right, and if I use a proper blocks that are available on GNU Radio, I'll be able to make an amplitude modulated transmitter. So let me walk you through the equation. All right, so if you were to look at the equation on top, this is an equation for your amplitude modulated signal. We have a signal that has an amplitude of AC, that is your carrier signal, that has a frequency of FC. Plus in a bracket, you have 1. This is just to make your signal go up, that's it. Plus some Ka factor multiplied by M of t. M of t is your modulating signal, which is your information signal, and that is given as AM cos 2 pi FMT. It has some modulating frequency M of t, FM, and some amplitude AM. And this Ka factor is actually a modulation index, and modulation index basically defines what is the depth of your modulation. So this value can be anywhere from 0 to anything more than 0. So why am I saying this? Because if you want your signal to be 100% modulated, so this value can be from 0 to 1. But sometimes there could be an overmodulation in the system. And that overmodulation system can be defined when your modulation index is more than 1. So anything above 1. So you want your signal to be 100% modulated. So this value can vary from 0 to 1. And if it's less than 1, then this signal is undermodulated. This factor will tell me this. And if it's more than 1, it's overmodulated. So what have I done for you? I have just actually just simply transform this equation. I just multiplied this carrier signal to these components, and this is how your equation would look like. So this is your modulation term, carrier signal, that and this is being distributed here. That's why I have this term, and plus I have these two components. So in place of my modulating M of t, I have written cosine 2 pi f M of t. It has an amplitude AM, and this is just some multiplying factor. This is multiplying both of these components. So using my trig identity, which is cos of A times cos of B, which is 1/2 cos A plus B plus cos A minus B, simply applying this, you will get this. So according to this definition, your spectrum should have a carrier component with some amplitude. You will have a modulated signal which should consist of FC plus FM frequency and FC minus FM frequency. This equation, when I distributed this term and applied my trig identity, this is what I should see. And so let's try to observe this signal. So what I'm going to do, keeping this equation in my mind, I'm going to make a flow graph. So what I'm going to do, I'm going to open up my GNU Radio, which is open. And I'm going to simply go to my GNU Radio, which is right now it's open, right? And what I'm going to do, so I'll have a PowerPoint right here. So this is the equation that I want to make, which is AC 1 plus K M of t. So as you know, in maths, we like to solve the bracket first. So the first thing I'm looking at is actually I have my modulating signal, which is M of t, that is being multiplied by some factor Ka, which I am calling it modulation index. So I'm going to take a signal source, go here, I'm going to type my signal frequency, and I'm going to pick up my signal waveform. I'm going to leave it as cos. I'm going to click on it, and I'm going to leave everything as is. Okay, this thing is being, according to my definition, this thing is being multiplied, this M of t is being multiplied by some multiplication factor that can take values from 0 to 2. Why more than 1? Because I want to show over modulation. So I'll just simply go here and I will type in my multiplier, because this thing is being multiplied together with this signal. So I need some type of a multiply block. So just simply, so you're multiplying it with some constant value. So I'm going to have this multiplication factor. and this thing has a constant of 1, so I'm just going to leave this as is, and I'm going to simply plug this in here. So my modulating signal is being multiplied by a multiplying factor value, which is this guy. All right, so I'm just going to simply connect this flow graph. I'm going to change this from complex to real number just to make my life easier, and just to show you the concept. You can also do it with complex, that's not a problem. And the next step in my equation, if you see the whole thing which is being multiplied, there is an addition of some value 1. So it's mean I need to add something. So you need an add block. Just simply go here, add. You're adding a constant value of 1. So I'm just going to simply come here. I'm going to change this to my float value so I don't get error in my flow graph. And just simply I will connect this as is. I'm going to change this value to 1 because in my equation it was saying it's just 1. Now the next thing is, this whole thing, once you have solved your bracket, this whole thing is being multiplied by a cosinusoidal frequency of Fc. All right, so I'm just going to take another block, signal waveform generator block. I'm going to bring this over here, which is defined by this term. So in order for me to represent this, this is what it's representing, and this whole thing, this answer of this whole thing is being multiplied by this value. So I'm going to pick up a multiply block. Multiply. So I'm going to use this block, multiply, and I'm going to bring this block in, and the output of this guy would go in, and output of this guy would go in. Let me change the value. Let me just change this to float, so everything is in real number. Now, if you were to compare your equation with the graph, this should look exactly the same. Why? Because in the bracket I have some multiply value which is being multiplied by my signal source, which is your modulating signal, and something is being added to it. So I'm just simply adding it, and the whole thing, this whole thing is being multiplied by this block, which is your carrier frequency, which is being done here. That said, this is a simple FM AM transmitter. This is how that simple it is. So now what I'm going to do, I'm going to see the output. So when you're just doing simulation, you need to add throttle block. If you don't have physical device connected, for example, like your USRPs and other things like that, so you need to add a throttle block. It actually controls the samples which is coming out from your PC. Just a throttle block right here. This is, you need to do it anywhere in the flow graph. All right. So once this thing is done, and so now what I'm going to do is this. I'm going to look at this signal in my time sync. So I'm just going to simply look for my time sync, which is right here, time sync QT GUI, and I'm just going to connect this. And I also want to look at this signal in frequency domain as well. So I'm just going to simply bring my frequency domain sync, which is right here, QT frequency sync. All right. Let me just move this over here so you can clearly see. So once this is connected, let me just connect this. And okay, hold on a second. So this is connected. I'm going to change this to float. So everything is in float. Okay, this is float and this is float. So we're good to go. That's it. We don't need to do anything else except for one thing. So this is what my modulating frequency is. So I'm going to change this frequency, let's say to 1K is good enough. And I'm going to change my carrier signal frequency to, let's say, 100K. Right? That's the only change I'm making. And the rule of thumb is this: when you're modulating signal, your carrier signal should be at least 10 times bigger than your signal, your modulating signal. Second, I want to do is this, because the sample rate that I have right now, the sample rate that you're seeing right now is 32K, and I have a signal that is 100K. So at least I want to have twice of those samples. So I'll just simply change this to 256K. All I'm doing, I am just changing the sample rate to 256K. So let me just click apply and OK. So my flow graph is good to go. As per the equation, I just simply looked at my equation and I just transformed that equation in the form of a flow graph. Now the next step is just to simply run it. So I'm going to run this flow graph and see what's going on. So I'm gonna call it AM1. All right, then we're going to make some changes to it. All right, so now here we go. So this is how your graph is looking like. So if you were to look at it, this is somehow similar to what you normally see in a form of graph and things like that. Now the thing is, I won't be able to manipulate anything. Normally you should see a spike. As per our definition, I would see an FC plus FM component and FC minus FM component. As you can see, once we have worked out this equation, this is what we normally see, and this is how a typical flow graph would look like. You will have, so this is 100% modulated signal. As you can see, there's nothing here. You can do a maximum value minus minimum value divided by maximum value minus plus Vmax minus Vmin, Vmax plus Vmin. That should give you a value of 0 here. So now I'm not seeing that picture clearly. So what I'm going to do a few things. So there's I can use a QT range block to actually change things like, you know, live. So what I'm going to do, I'm going to go here and I'm going to type in my range. All right, so I need a couple of these blocks. Actually I need 4 of them. All right, so the first thing, I want to have this freedom that I'll be able to change this frequency. The first, I'm going to call it FM for my modulating frequency. And I want to have this modulating frequency, a default frequency of, let's say, 5 kilohertz, 5 e to the 6. All right. And I'm going to call these values here. And I want to have a default frequency of 1, start frequency from 1 e to the 3, and let it go from 1 all the way up to 10 kilohertz. All right, and I want to go in terms of a 100 hertz of band, 100 hertz of a step size. All right, so this is FM. So I just call this FM, which is for modulating frequency, and this is my modulating frequency. I'm going to simply go here and I'm going to call it FM. So now when I run the flow graph, I'll be able to change my modulating frequency using my slider. And okay, let's just close this. Now at the same time, I want to also do the same here with this. All right, let me see what is the value. All right, so just quickly change. I want to change this value as well. So I want to start off with so if the starting frequency is 1, at least I want to have 10K. So let's have a default frequency of, sorry, let's call this first FC. Apply, and then use a variable block like this, and let's just call this FC for carrier frequency, and let's have a default frequency of 10 kilohertz. Let's go like this. The starting frequency of 5 kilohertz, 5 e to the 3, and stop frequency at about 100 kilohertz. Sorry, 100 kilohertz, and a step size of 100 is fine. Okay, apply. So this is being called here. Now the next thing I want to do is this. The other thing that is also controlling, which I called it a multiply constant value. If you were to look at it here, this value Ka is actually a modulation index. So I want to control this modulation index. So what I'm going to do, I'm going to get one of these sliders again, and so I want to get one of these sliders again, and I want to call this a MI for modulation index, and I want to set these properties to be, let's have a default to be, let's say 0.5. Let's go like default has to be 100% modulation, and let's go from 0 and go all the way up to 1.5 in an increment of 0.5. I don't know, something like that. So default value is 100% modulation, and starting value is from 0 and all the way up to 1.5. So I can see over modulation. This is actually a multiplying factor that would help me control my modulation depth. Okay, let's simply apply. All right, what else do I need? That's it. My flow graph is quite complete. And oh, sorry, I need to call this here. So just simply go here. I'm going to simply type MI for modulation index. If anything was wrong in this flow graph, you will see it in the form of a red block. But I think we're good to go. Now let's just simply run this simulation. And let's see what's going on. Alrighty. Okay, that's fine. That's fine. Let's see how I can control this. I want to see, okay, so modulation index, I'm not going to touch this. What I'm going to do, since this is a default frequency, I'm going to start increasing frequency because my carrier frequency is too low, my modulating frequency is too high. No, it is, but it's not actually a factor of 10. So what I'm going to do, I'm going to just reduce my frequency to, let's say, something like 3 kilohertz. And now I'm going to start increasing my frequency. And if you can clearly see this start taking place, and you can start seeing those components which I promised that you would see according to your mathematical equation. You would see an FC plus FM term, FC minus FM term. So now, since I know what is my modulating frequency here, it's 3 kilohertz. All right, let me change this carrier frequency to 17 kilohertz. All right, why? Because so I can tell you that indeed this is happening FC plus FM and FC minus FM. So if my modulating frequency is 17 kilohertz and this is my my carrier frequency is 17 kilohertz and my modulating frequency is 3 kilohertz, then FC plus FM should be 20 kilohertz, and indeed it is 20 kilohertz. All right, and FC minus FM, so 17 minus 3, so I should get 14 kilohertz. All right, 14 kilohertz as is, right here. And as you can see, so these are FC plus FM and FC minus FM component with some amplitude. And you also have a component which is just your pure carrier signal. And this is lying at the center. If you were to look at it, isn't that amazing? That is 17 kilohertz right here. Why you're seeing the negative frequency? Because, as you know, because of Euler's identity, Euler's identity also have a negative frequency part. But in physical system, you will be only able to see this part of your component, which is going to be your actual component as per our equation, this carrier signal, which is right in the middle, 17 kilohertz. Then you will have FC plus FM component, which is right here, which is FC minus FM, which is going to be right here. So this signal is 100% modulated signal because this is 1. Now let's try to under-modulate our system by just changing the modulation index. When I change the modulation index, now as you can see, this is no more in the middle. This is no more as 0. This is some value, which is going to be whatever that value is, 0.55. So 1 minus 0.5, 1 plus 1.5 when you divide this. Now, so this is at 0.5, 50% modulated signal. Now, when I look at over-modulated signal by just simply increasing this frequency, so this is 100% modulation index, where this guy is simply 0. And by changing it to 1.5, just notice it here. When I change this to over-modulated system, this here you will see a phase reversal. This top part will go on top, bottom, and the bottom part will go up. Just simply look at it. You can see the flip on this signal as well. So this is the idea behind how you can actually, so now by connecting your USRP or HAC RF, you'll be able to transmit this tone in air. So this is how easy it is, that how you can transform from a mathematical equation from your book into a working system that will help you prototype different type of radios using GNU Radio Companion and software-defined radio. I can also just do one more thing. I think the distance is 2. So let me just change this MI from 1 and go in a distance of about 0.1. So now, when I look at my system, let me quickly run the simulation and let's just change this frequency to 3 kilohertz and just increase my frequency to, I don't know, whatever the working frequency is. All right, let's look at it here. All right, I just want to see it. Okay, let's look at this. I can just simply look at it. Now, this is 100% modulated signal. Let me just zoom in. Now let me change this to something else. Here we go. So now you can see a over-modulated signal. Now let's go to 100% modulated signal. Now let's go to 90%. As you can see in the middle, this is no more 0. And let me just come completely. So this is under-modulated signal. And once you don't have that modulating signal, modulation factor, you will just get your carrier signal back. That's it. It's how that simple. And then when you apply modulation by changing modulation index, here we go. Modulation is happening and you start seeing your envelope that is associated with your flow graph. The envelope that should be there for your AM signal. So I hope you like this small tutorial on software-defined radios and especially AM radio. And if you have any questions, please leave it in the comment section and don't forget to like and subscribe to my channel.